Okay, so we know about energy, right? Last week we know about energy. The units is in joules. We learned about kinetic energy, which is energy associated with motion. So there is also this thing called the potential energy. It is the energy associated with the position. That's our gravitational PE. PE is potential energy in short, or configuration, which is our elastic PE. Okay, so we also have briefly seen what is elastic PE already. Remember our springs, when you stretch the spring, you will have some energy, right? According to how much you stretch, which is the X, right, that we were looking at. So that's already our elastic PE. We'll talk more about it in this topic. P can be considered as stored energy that can be converted to Ke or other forms of energy. So what is gravitational potential energy? Consider an object moving downwards from y1 to y2. So this illustration here, right? We are at y1. Let's say it moves down to y2. Okay, so it's a distance of delta y. So if we have an object, right, we apply some force. The work done by gravitational force is given by this formula. Okay, so the object is moving this distance. That's our delta y. The force that we are looking at here, right, is the gravitational force. Okay, of course, in real life, of when you release an object, you drop down, right? This is because there is force pulling it down. Okay, and that's our gravitational force. If we are to go and calculate the work done for this, which is energy, right, it will be F dot delta y. And remember our dot product, we revised it, right? So if we have our dot product, it will only consider values that are parallel to each other. Okay, so in this case, the object is moving down, the force is also pointing down very nicely in the same direction, right? So it will work out. Later we will see if they are not exactly in the same direction, it won't be counted. Okay, but in this case, in this simple case, we will have this mgy1 minus mgy2. Okay, y1 is here, y2 is here. So the work done will be mgy1 minus mgy2. If m is moving upward from y2 to y1, the work done is given by the same formula, but it will be negative. So if we have the same object, because gravitational force is still acting downwards, if we have the same object moving from y2 to y1, they're going to get the same magnitude, just that there will be negative sign in front. Okay, that's what the third point is talking about. So we have seen this, right? Mgy1 minus mgy2. This mgy that we are talking about, right? This is our gravitational potential energy. Okay, mgy. Sometimes we also write it as mgh. Actually, it's the same thing now. Okay, so h stands for height. It's the concept that's important. Okay, so you can either write as mgy or mgh as long as you know what you are referring to. Basically, this is the distance. Okay, the difference, the distance. So work done, total work done, which is the work done by gravitational force, will be U1 minus U2. U1 here, right, we are referring to the potential energy. U is the potential energy. And then if we relate to what we had learned in the previous lecture, topic 7, right, work energy theorem, remember the total work done is delta K. K stands for kinetic energy. So delta K, right, that means kinetic energy at the final position minus initial position. Okay, so it's also equivalent to this. If you equate the two together, you are going to get something like that. Okay, K2 minus K1 equals to U1 minus U2. So if you shift it around, you will get this K1 plus U1. Basically, this is the total energy at the initial state equals to the total energy at the final state. So this is actually a statement for conservation of energy, right? So if you expand it out further, so this is more usable in a more usable form, right? When you are given problems, you will likely use this kind. Okay, half mv square. This is kinetic energy for the initial state plus mgy1. This is potential energy for the initial state, then equals to the same thing but for the final state. Okay, in other words, energy initially must be equals to energy at the final state. Any questions so far? Okay, should be okay lah this part. But anyway, if you all got any questions, just feel free to type in the chat. Okay, if I see, I'll answer. Which I'll see lah because I have two screens here. Okay, and I teach at home. Then we come to gravitational PE along curved path. So just now, right, the object travels from y1 to y2, which is moving directly downwards. So what if the object is moved along this curved path? You see, you bring it down, but you also bring it slightly to the right. What happens? What happens to the gravitational PE? How do you compute that? So let's look at this. The work done by gravitational force is mg. Very familiar with that already, right? Then this j, right, is the unit vector, which denotes the direction. Also very familiar with that already from our kinematics. And because this is a 2D issue, right? We are moving down and moving to the right. So we have our vector in vector form. We have one in the x direction and the other one in the y direction. Okay, now you apply the same formula again. Remember, work done, the energy. Now we want the energy. That's why we go and look at the work done. Work done will be you take the force dot the displacement. Okay, so here you will take the force dot the displacement. But remember our dot product, right? It will cancel out anything that is perpendicular. It will only keep the values that are parallel in direction one another. Okay, so whatever you see, it ends up with minus mg delta y here, okay, which is exactly the same as before. So you realize whatever that is in the x direction, right, it gets cancelled out. Because if you take j dot I, it will just cancel out. Okay, so we are left with this. So if you write out the formula again, it's going to be the same as the previous case, the previous simple case, which is u1 minus u2. What can we tell from this, right? Work is unaffected by any horizontal motion. So if you're going to move the object from here to here, the change in potential energy, right? You just need to look at the height. Okay, the difference in height. The x direction will not matter at all. You can also see as if you have something here, right? Let's say you move it directly to the right. Okay, move it directly to the right. You never move up or down, right? You move only directly to the right. There will not be change in gravitational PE. Okay, because it's unaffected by any horizontal motion. And also for gravitational PE, right? Only the positions of initial and final points are important. So what this means is only the difference is important. Okay, we always look at the difference. From here to here, what is the difference? We don't really care about the absolute numbers at the top and at the bottom. Okay, it doesn't matter. Only the difference will matter. Okay, some characteristics of gravitational PE. Only the change matters. Okay, only the change matters. So this means that we can place the origin of coordinates in any convenient location because only the change matters, right? Usually we will place the coordinate at where the bottom point is. Let's say you move the object from here to here. Usually we will treat the bottom point as 0, so easier. Let's say this is 1 meter, this is 0. You know that it's 1 meter already. But if you want to challenge yourself, right, and place the coordinate somewhere else, you will get the same answer also. Let's say you treat here as 3, you treat here as 2, you will still get the same answer. Because in the end, only the difference will matter. Okay, but don't challenge yourself, okay? Try to, when you work out your solutions, right, make your life easy. So at the object at the bottom point, right, try to take that as the 0. So don't confuse yourself, okay? Horizontal motion does not affect the value of Wg. Okay, so horizontal, again, it does not affect, only the vertical one. The unit of gravitational potential energy is the same as that of work. So when we have energy, right, the units will always be joules. Potential energy is a scalar quantity, same as kinetic energy. Scalar means it has no direction. It has only magnitude. It has no direction. Sometimes we will see a negative sign, but that does not mean it's pointing in the opposite direction. Okay, if when we are dealing with energy, right? If we see negative sign, means energy is taken away from a system. You deduct it from the system. Okay, it does not mean it's pointing in the other direction because it's just a scalar, not a vector. So in that sense, some students will feel that energy is easier than forces. Okay, because there is essentially no direction to this topic. Work done by gravitational force depends only on its initial and final vertical coordinates, so it's path independent. Gravitational force and the force that spring exerts are both conservative forces. The energy stored as P can be converted back to kinetic energy. So when we talk about conservative forces, right? As the word suggests, this kind of energy, right, it can be converted back easily to another form of energy. Okay, for example, why we say gravitational P is conservative force? Because when you are at a height, right, you are at a higher height, you have a higher PE. All right, if you release this pen, let's say this pen, I release it, this gravitational PE, right, it will lose height, correct? So it will lose gravitational PE, but the speed will increase. It will get converted to kinetic energy. Okay, so it's easily converted to other forms of energy. Okay, this simple act of dropping a pen, drop a pen, it's converting potential energy to kinetic energy. Okay, so these are conservative forces, easily converted back to other energies. So the other kind, right, they are non-conservative, which means the opposite. So for example, like friction and air resistance, these are dissipative forces. So mechanical energy reduces when acted upon by these forces. When we go and you go and push your laptop across the table, friction will act, correct? The friction will act. And then the friction, right, will convert some energy to heat and sound, all that. So it converts energy away to heat and sound. It's very difficult to convert back the heat and sound to movement, correct? It's very difficult to convert back. Of course, with engineering, you may be able to convert back, but you get back some of the energy. But fundamentally, it is non-conservative. It does not get converted back naturally, or rather so easily. Okay, so these are non-conservative forces. So some properties of conservative forces. A force is conservative if the work it does on a particle moving between any 2 points is independent of the path taken by the particle. So it's illustrated here on the right. If you are at point A, you try to move to point B, right? If you take W1, this path, or you take W2, another path, or you can have as many paths as possible, they will all be the same. Okay, it's independent of the path. Only depends on the start and the end point, which is the same. Okay. Work done by a conservative force exerted on a particle moving through any closed path is zero. So it's illustrated here. If you are moving from point A to point B, and then you go and move from point B back to A, right? Also, it does not matter. The path will matter. If you go and move from A to B and then back to exactly where A is, it will be exactly zero. Okay, the work done will be exactly zero in the most ideal situation. Okay, actually, this property and this property, they are sort of describing each other also. So now, I have another concept question for you all to think about. Three identical balls are thrown from the top of a building, all with the same initial speed. The first is thrown horizontally. This is first one. The second at some angle above the horizontal. The third at some angle below. So we throw down at some angle. Neglect air resistance, rank the speeds of the balls at the instant each hits the ground. So imagine the ground is at the same level. Imagine the ground is at the same level. So when the ball hit this level, right? When the ball hit this level at the same height, rank the speeds. Which one do you think will be fastest or slowest? Of course, the answer is in the next slide, but take a minute to think about it, because if you get this right, that means you roughly get the idea of this entire topic already. Okay. So the answer is they will have the same speed. Why? Because using this equation, which is the conservation of energy, you see they start from the same height, correct? They start from the same height. So this height all the way to the same height at the ground, they all lose the same height. All right, they lose the same height. So they will have same amount of same amount of potential energy that gets converted to kinetic energy. Okay, we're talking about the concept first. Same amount of potential energy gets converted to kinetic energy. Okay, and we know kinetic energy is half mv square, right? If half mv square is the same, they are going to have the same speed here. Okay, which is the v that we are talking about. They are going to have the same v. If you write out in equations, it's something like that. Okay. Any questions? Or you need me to explain one more time? And just let me know. Okay, okay, good. And let's take a look at one example. A man with mass 70 kg sits on a platform suspended from a movable pulley and raises himself at constant speed by a rope passing over a fixed pulley. So it's illustrated here again on the right. The platform and the pulleys have negligible mass. Assume that there is no friction loss. Find the force he must exert. And part B, find the increase in the energy of the system when he raises himself 1.2 meters. So we do part A first. So part A, find the force he needs to exert. Force, right? When we see force, what's the first thing they should think of? Free body diagram, correct? The time when we talk about forces, always the first thing you do is draw out the free body diagram. Okay, so this question here, right? You going to ask yourself, how should you make the cut to draw the free body diagram? You want to isolate this body, which himself. You want to isolate it. So naturally, you will make a cut above him, somewhere above him. Okay, so if you make a cut here, if you make the cut here, then you draw the free body diagram of this isolated body that's below. So down here is the isolated body, right? You must always draw the exposed. So you make a cut, right? You cut through three ropes here. Okay, so you need to draw T pointing away from all these three ropes, all point upwards, okay, in the vertical direction. Then, of course, you have this, always have this mg pointing downwards. You can also write as w, up to you. Okay, you always have a weight going downwards. So is that all? That is all. That's all the forces that you have. So now you can go and take summation of forces. Consider the system as man plus platform plus movable pulley. So if you take summation of forces in a y direction, you will get 3t, because there's 3t, right? Pointing upwards, minus w, because w is pointing downwards. That is our F. Okay. Then the other side will be 0, because we assume acceleration is 0. Okay, so from here, you can solve for T, which is 229 newtons. Okay, then moving to part B. Okay, part B is find the increase in energy of the system when he raises himself 1.2 meters. Means he's now sitting here, right? He is pulling this rope. You can see all the construct of the rope is going over the first pulley and then going over the second pulley, which is connected to him and connected back to the first pulley. So if he pulls on this rope, right, you can imagine him going upwards. Okay, so the question is, when he goes up 1.2 meters, what is the increase in energy of this entire system with him inside? The first method, we use what we have learned so far in the topic, which is the easiest way. Since there's no change in speed, when you gain height, right, means you gain potential energy, correct? That's the only energy that's involved. So the gain in energy will be your mg change in height. Okay, so in this case, it will be mg, your m is 70, g is always 9.8 times 1.2 meters, because the question tells you 1.2 meters. So this is the change in energy. In other words, gain this amount of energy. Okay, this part should be okay for most people. Let's look at the second method, which is more complicated, and then need to visualize it and then think more logically. So let's follow this. If the movable pulley moves up a distance s, movable pulley means this one. If it's moved up s, that means he will move up s also because it's connected to him, right? Then both rope segments A, B, and CD must each shorten by s. So you see this pulley here. If it moves up by s, that means this AB, this rope section, right? This rope and CD, it will get shortened by S. Right? Because this pulley gets closer to the other pulley, so it will get shortened. Okay, that's the first thing. Any point on the rope segment EF will have to move down. EF is the one that he's pulling. Why will it move down by a distance of 2s? Because you see AB is shortened by S, correct? CD is also shortened by S. This length of rope, right, that is shortened by the two short ropes must go somewhere, and it will go into EF, correct? That's why it will move down a distance of 2s. Yeah. Then the man has also moved up a distance S. In this question, S, the S that we are referring to is that 1.2 meter. So relative displacement of man relative to the rope he is pulling would therefore be 3s. Because you see here, he himself moves up 1.2 meter, which is a distance of s. But at the same time, this segment EF, right, is moving down because he's pulling it, correct? It's moving down a distance of 2s. So what is the relative displacement? From his point of view, from the man's point of view, right, he is pulling the rope 3s, a distance of 3s. So he pulled down the rope 3 times of s. Therefore, the work done by his force, will be the force times distance. Okay, so force is the tension that we have calculated in part A times the distance. In this case, the distance, right, will be 3 times of the s that we are talking about here, which is 1 point. That's why we take T times 3 times 1.2. You will get 823 joules. So this is the work done, the work he is doing to the system. Okay, you will take force times distance. And you will get the same answer also, 823 joules. Okay, then if you look at these two, right, they are the same. It also tells you that the work that he's doing to the system is all going to the potential energy of the system. So he add energy to the system, right? All this energy, it goes into the potential energy to help him gain height. Okay, which is conservation of energy. Okay, no questions, huh? Okay, good. That is gravitational PE. Now we come to elastic PE, which is not something new to you because we have seen it before. Just that we talk more about it. Okay, so elastic PE is half kx square. This is our elastic PE, half kx square. There will be no negative value. We cannot arbitrarily assign zero value to this elastic potential, energy. Okay, remember just now gravitational PE, we can assign a zero value to the one lower in height, right? So makes our life easier. But for elastic potential energy, we cannot anyhow assign a zero value. So the zero value, right, it must be when the string is neither extended nor compressed. So this is our energy versus the displacement graph. When the spring is at equilibrium, that means you never stretch it or compress it, right? It will be at zero energy. Okay, and that must be always where zero is. Zero will always be at the equilibrium. You cannot anyhow define zero to be here. Zero also cannot be here. Okay, zero must be where the equilibrium is. That means you haven't go and touch the spring yet. It's not stretched, it's also not compressed. Okay, then you go and stretch it, you will increase the energy, correct? According to how much you have stretched. The x value, half kx squared is the energy, right? So if you increase x, potential energy is going to increase. The elastic potential energy. If you go and compress, it's also going to increase. It's only when you do nothing to it, when it's at the equilibrium position, that it has no potential energy. Okay, that's why zero must always be here. Yeah, that's what the third point is talking about. We assume that spring constant is the same during compression extension unless stated otherwise. So spring constant is this K here. It also has other names, like sometimes we call it the force constant. Okay, so basically this K, we will assume is the same. So this will look like a nice curve. But in real life, not all springs will behave this way. Sometimes it's easier to compress than to extend, or vice versa. Okay, then this will not look like a nice smiley like this. Conservation of energy. The work done by the spring will be half kx1 square minus half kx2 square. Basically, the difference in the potential energy, right? Half kx squared is our potential energy. Elastic, you can also write it in this form. U is our potential energy. So elastic potential energy is a form of potential energy. Gravitational potential energy is also a form of potential energy. So they all fall under U. So U1, right? If you write U1 like this, right? Maybe inside it has elastic potential energy and also maybe it has gravitational potential energy. If we combine with kinetic energy, right? For springs only, for spring only, let's assume that there's no change in height. The conservation of energy equation will look something like that, which is, if you are familiar with the concept of conservation of energy, right, you don't even have to memorize this at all. Okay, you just need to know the energy at the start must be the same as the energy at the end. If there are no energy losses, of course. Okay, so this is our kinetic energy at the start, elastic potential energy at the start. This is the kinetic energy at the end, elastic potential energy at the end. Okay, conservation of energy. The next slide, this is actually reinforcing and repeating almost exactly the same thing. We learned that total mechanical energy consists of the kinetic part and the potential part. So if we don't have other non-conservative forces such as friction, in other words, if we don't take away energy from the system, right, then energy at the start will be equals to energy at the end. So if you rewrite it, you can write it in this manner. Ai, which is initial kinetic energy, plus Ui, you see a summation here, right? Because inside can consist elastic and the gravitational part. Okay, so can have both components. Okay, but basically your main takeaway, right, should be the starting total energy must always be equals to the energy at the end. Okay, this is our conservation of energy. may also be denoted as this form. This is the equation, same equation. Sometimes we can also write it as T1 plus V1 equals to T2 plus V2. So just like our previous topics, right, there may be different representation, different letters to represent the same thing. So some people can represent kinetic energy using T, okay, and then potential energy using. It's up to you to use what letters you want. Okay, this is just to let you know some different people use different letters. So next time at work, right? Maybe at work or when you interact with others, you see different letters, you know it is denoting the same thing as long as you know the concepts. Okay? So this is the same because potential energy, right? Inside may have gravitational and elastic. So you have an additional term. Let's take a look at another example. A variable force F is maintained tangent to a frictionless semicircular surface. By slowly varying the force, a block with weight W is moved, and the spring to which it is attached is stretched from position 1 to position 2. The spring has negligible mass and force constant K. The end of the spring moves in an arc of radius A. Calculate the work done by force F. So initially, you are at position 1, which is here. Then you apply a force, right, to stretch this box, to stretch the box upwards. So initially, you are somewhere here, right? Then you go and stretch the box using a force F, and you apply according to this arc. Okay, so this is the, you can say that the distance travel, right, is the arc. All right, so you will need energy to pull the spring, and then you also need energy. You also need to overcome the gravitational PE part, right? Because you are lifting this box from a lower height to a higher height. Okay, so there's spring involved. There's also a lifting in object involved. Calculate the work done by force F. So the spring is stretch and extension of this. That means from here, position 1 to position 2, what is the distance traveled by the spring? It's given by our A theta. A is our radius. Okay, so remember our arc length is equals to our R theta. And remember this theta, because we don't have any cosine, sine, tangent, all this, right? If you don't have all those, this theta, we must always put it in radians form. Okay, you cannot be in degrees. Okay, it must be in radians. Okay, so this is the distance. Our elastic potential energy, right, is therefore given by this. This is from our half kx squared. X is the distance traveled. You know the distance is a theta. That's why down here inside is a theta. Okay, so this is our spring part. Also, we know that the mass m is lifted up by a distance of this height. Because from this height to this height, there is a distance, right? Okay, so the distance that we're looking at is this one. To here. This is the distance that we are looking at. Remember, for gravitational PE, we don't care how much it moves to the side. We only care about the up and down, right? How much it moves up and down. So we only want to know this distance. And what's this distance? We know that A, the radius. We also know this angle, right? To get this distance, it's basically just A sine theta. Okay, trigo. The same trigo in our forces and kinematics. Okay, so if you are dealing with something using the opposite, right? Always A sine theta. So with this delta y, which is change in height, we can get our change in gravitational potential energy, which is mg, change in height, right? So this change in height you sub inside here. So the work done by this force, right, is simply adding these two up together. Okay, from the conservation of energy. Okay, because the work that you do to this block, that means the energy that you supply to this system, right? The work done, it must go into stretching the spring plus bringing the box up this height. Okay, this PE, this gravitational PE. That's why you take this plus this. Okay. Yeah, I have no questions. Then we move on. We come to non-conservative force. Most common one is our friction. So friction, as we all know, it takes energy away from a system. So suppose an object given an initial velocity vi slides on a rough horizontal surface for a distance d before reaching final velocity. That means this scenario is illustrated here. So imagine you have a book. Initially you have some velocity. After it slides a distance, right, you have another velocity. And because of friction, you know this VF will be a smaller value, right? But they have different magnitude. So the change in kinetic energy is half mv square using the final state, minus the half mv square of the initial state. Okay, so the change in energy, basically the energy at the end minus the energy at the front. This change in energy, right, must be equals to Fd with a negative sign in front. Okay, so this statement, this equation here, you can see it as the energy that is the difference in energy must be the amount of energy taken away by friction. Okay, so whatever energy the friction take away, right, will be the difference in energy. Okay, conservation of energy again. So loss in Ke is FKD. This K is kinetic. I remember we have our kinetic friction and our static friction, right? Because this book is moving, so we are talking about FKD. Or if you just remember it as FD is also fine, which is the energy dissipated by the force of kinetic friction. Part of the energy is transferred to the internal energy of the block and part to the surface. So you see this book, right, from a fast speed, after a while, right, after this distance, it is moving at a slower speed. So it loses energy, right? The friction takes away this energy and convert it to other forms. Convert it to heat. That's why when you rub something against another surface, right, you are going to get heat out of it. That's why in winter countries we rub our hands, correct? Okay, you're making use of the friction to generate heat from the motion. Convert to heat, also convert to sound energy. The sound that we hear, they also have some energy values. So some go into sound, and also energy can also go into deforming the item. Okay, so maybe from slide from here to here, right? There's some changes along the bottom surface. Okay, go into deforming the object. You change the shape of the object. That also requires energy. So energy is taken up by friction to do all these other stuff. Okay, which could be unwanted lah. Right? Usually heat, sound, all this is unwanted in most of the time. Okay, but from energy point of view, this is how it works. Okay, the total energy must be the same. Conservation of energy in general, total mechanical energy is conserved when conservative forces act within a system. Thermodynamics, energy lost by non-conservative forces, for example, friction, can be converted into internal energy in the body. When we talk about internal energy in the body, we are referring to the rise in temperature associated with atomic vibration. At this point of time, because most of you, you are just you all have just started this course, right? So you all haven't come to this thermodynamics yet. So next time when you all study thermodynamics, you also will encounter a lot of energy concepts. Okay. internal atomic motion has Ke and Pe also. Okay, just for knowledge lah. Okay so far? Everyone okay so far? Then we come to potential energy function. Okay. So literally this potential energy function, right? It is a function to describe potential energy. The function, as we know, is like some equation, right? Maths. So this equation can be used to describe potential energy. So since work done by a conservative force is a function only of a particle's initial and final coordinates, we can define potential energy in this form. So the one on top here is a more general form. That's why we have R here. So potential energy equals to integral R naught to R F dot ds. You can see this F dot ds, right? Is actually your work done formula, which is equals to energy. So from dimensional analysis, which we had gone through in the first lecture, right? You see they have the same dimensions. Okay? This is basically work done plus U naught. U naught is usually the reference lah. When we put naught here, usually it refers to the initial state. Okay, so if U naught means refers to the potential energy at the start. Then in 1D, it's actually the same equation, but in 1D, all these R, right, and S, it will change to X because we are only in one direction, right? So this may be easier to understand. We are only looking in one direction along one line. The equation will look something like this. U naught is often taken to be zero at some arbitrary reference point. Only the change in potential energy is physically significant. So this U naught here, in the general form, it will be there. But for potential energy, let's say gravitational potential energy, right? We will take the lower one, which is the reference, to be zero, make it convenient. Conservative force in 1D, integral of f dx, this is work done. This is change in potential energy. In differential form, you can also write it in this manner. So what we will get, right, is f equals to minus du over dx. This means that if you go and differentiate, if you have a graph that's plotting out potential energy, if you go and differentiate that, you are going to get the force. Okay, this is how force is related to the potential energy. So let's see whether that equation is true. For spring force, right, we know the spring energy is half kx squared. So if you go and differentiate that with respect to x, half kx squared, you differentiate respect to x, you're going to get just kx, negative sign in front. Okay, so it's correct, right? You differentiate the energy, you get the force. Gravitational force near surface of Earth, we know the gravitational energy, potential energy is mgy, right? If you go and differentiate with respect to y, you're just going to get minus mg. Okay, so energy, force, which is correct also. Okay, the last one here, now maybe you haven't seen this before, but those who had taken some form of physics last time, maybe you're familiar with this, but don't need to worry for now. At the end, we will touch this. Okay, is gravitation. This is for gravitation when we are talking about objects that are far from Earth. Okay, maybe you compare moon and the they are so far away. That's why we have another formula for it. This one, when we talk about mgy or mgh, right? We are assuming they are very close to the Earth's surface. We are all very close to the Earth's surface now, okay? Let's take a look at another example. A certain spring is found not to obey Hooke's law. It exerts a restoring force given by this if it is stretched or compressed. You see F equals to this weird thing here, right? Then you know it doesn't obey Hooke's law already because we know Hooke's law is just kx. Very simple, right? But this one got x, also got x squared. So it follows this weird expression over here. Does not obey Hooke's law. And then they also tell you A equals to this value, B equals to this value. Okay, so A and B is known. The mass of the spring is negligible. Calculate the potential energy function for this spring. Let U equals to 0 and X equals to 0. This last statement here, right, is to make the U not disappear. So we set the reference and make it disappear. So make life easier for ourselves. So calculate potential energy function. It is given by this formula. So we will just use this formula to calculate the potential energy function. Okay, so basically, whatever is in the formula, right, you put it inside and then try to solve it. In this particular case, this fx is already given, this expression here. So you put this expression inside, and then what happens? You just need to perform a simple integration. All right, you have all the x here, dx. So you just perform a simple integration, and then you will get the answer. So this is the function to describe the potential energy for this particular case, this particular question. Okay. So very literally, potential energy function is really just a function to describe the potential energy. So at any value of x, right, you just put into this equation, you will know the potential energy at that point. Part B, which is continuing from the example, an object with mass 0.9 kg on a frictionless horizontal surface is attached to this spring. Put a distance 1 meter to the right. You'll take it as the positive x direction to stretch the spring and release. What is the speed of the object when it is 0.5 meters to the right of x equals to 0 equilibrium? So we go and put an object on the spring, we stretch it to the right by 1 meter. If you release it, what will happen? Of course, it will go back, right? You stretch the spring, now you release, you will want to go back. So the question is asking you, at 1 meter, now you release, it will go past this 0.5 meter mark, right? They're asking you at that 0.5 meters mark, what is the speed of the final, what is the speed of the object? So we can use the principle of conservation of energy to do this question. Okay. So conservation of energy equation is our K is our kinetic energy, U is our potential energy. Okay, so K1 and U1 will be on the left side. This is our total energy at one point, must be equals to the total energy at the other point. Okay, so the first point that we are looking at is at 1 meters. All right, at 1 meter, you ask yourself, what is the kinetic energy there? You stretch all the way to the other end. That is the maximum, right? It is not moving. That's why kinetic energy is 0. But there will be potential energy because you stretch it by that amount. Okay, so how to find the potential energy? Remember, we have this function which we had calculated in the previous part. Describes the potential energy, right? If we put sub x equals to 1, because it's 1 meter, we will know the potential energy at that particular point. Okay, so put this here, it will give you a value. That will be the potential energy at that point. Then you can look at the other side. K2 plus U2. This second point that we are looking at is 0.5 meters away instead of 1. Okay, so down here, because it's traveling halfway already, right? From the end, it's traveling halfway. So there will be some form of, there will be speed involved, right? If there's speed involved, there is kinetic energy. So you write the formula for kinetic energy, half mv square. M you already know from here. This v you put here, you don't know yet. That's why you want to solve it, right? This is what you need to solve. You just put here first. Then for U2, you have the potential energy function, right? You put it here, but now you substitute this x, right, equals to 0.5 because that's the position that we are talking about. Okay, then this whole equation over here, you see only V2 is the unknown. If you solve for that, right, you will get the speed that is traveling at that point. Okay. Then this last section, very quick one, just qualitatively only, for you to understand some energy diagrams concept. There's no calculation for this. So the motion of a system can be understood qualitatively through its potential energy curve. There are in general three types of equilibrium, and the force on the object is zero. When we talk about equilibrium, right, we know that it is not moving. Okay, there is no force acting on the object. That's why it's not moving. So there are three types. One is stable, the other one is unstable, the third one is neutral. Okay, so for stable is when Ux, this is potential energy, it has a minimum value. For unstable, Ux will have a maximum value. And for neutral, Ux will be a constant. In the next slide, right, it will be clearer. Okay, so this is the potential energy. Let's say we have a random curve here which describes some energy, right? So at the minimum points, we are going to have stable equilibrium. Okay, stable equilibrium. So what do you mean by stable, unstable, or neutral? So if we have a very simple object like a triangle, right? Stable means if you have this starting point, if you displace it a bit to the right, you displace it a bit right, it will return to its original position. Right, that's stable. On the graph, right, you can see as you are at this point, if you displace it a bit to the right, that means now your energy increase a bit, right? You will return to the lowest energy point. Systems tend to return to the lowest energy point. Okay, if you displace here, it's going to return here. So these are representations of stable equilibrium. For unstable equilibrium, is given by the maximum points. Okay, so on this graph, wherever there's maximum point, right, that is the unstable equilibrium. At these points, right, the object will move because it's in equilibrium, right? But the moment you displace it by a bit, it will start to go away already. It will find the next stable equilibrium. So an illustration will be the same triangle. If you go and try to balance it on this tip, right? Imagine we are in a very ideal environment. Okay, you balance on this tip, it will stay there if you never apply any force. But if you go and displace a bit to the right or left, it will not return to this position anymore. Okay, it will search for the next stable position, which is to fall down. Right. So if you look at this, if you displace to the right, it's going to search for the next stable equilibrium and then it's going to stay there. Okay, so this is how we see the energy diagram. So that's stable and unstable. For neutral, that means it's represented by the straight line here. It's not labeled. But basically, it's saying if you go and displace it, right, it will not move anywhere. You will just stay in that next position. It's neutral. So if you go and roll this circle, right, if you roll it a bit to the right, it will just stay wherever it ends. Okay, so that's neutral. Then this graph here in red is the force displacement graph. Remember, F equals to minus du over dx, right? F equals to minus du over dx. So if you go and take a du over dx, that means you differentiate this curve here, you are going to get, and you take negative sign, right? You're going to get represented here. Okay, so just for example, differentiation, you're finding the slope, right? So if you look at this point, the slope here is 0, all right? There's no slope. That's why the corresponding point below, which is the force displacement curve, will be 0. Okay, so they're just different curves. Okay, so this is all for topic 8. Any questions for this topic? So at the end, same thing, supplementary questions for you all to browse through. If you all don't know anything, right, then come and ask me. Okay. Okay, so topic 8, let's go to topic 9. We finish topic 9, then we take a break now, okay? So let's move on to topic 9. Oh, you all need a short toilet break. Also can lah. So maybe we will start at 7:35. Yeah, just enough for you all to take a short toilet break. Okay, 7:35. Later we'll take a slightly longer one. See you at 7:35. No problem. Thank you. Thanks, Michael. Thanks, Shaji. Okay, okay, let's start our next section. Topic 9. We're entering another section really. So we are out of energy anymore. Of course, energy is still related. So from forces, we move to energy. Now we are coming to this, um, could be new concept to some of you. It's called the momentum. So linear momentum, sometimes we denote using P, sometimes L. It provides information about the object and also the motion. Why we say object and the motion? Because the formula for linear momentum, right, is given by mv. Okay, momentum, or rather linear momentum. Linear means moving along straight lines. That's linear. The other kind which we haven't come to is angular, means rotating or moving circles, that kind of thing. But we are talking about linear momentum now. Okay, linear momentum equals to mass times velocity. That's the formula that we will be using when we come across momentum. So for linear momentum, we can also um, write out in different directions. Okay, so in the x direction, you can write out one using the velocity in the x direction, and then same for y and z. Okay, mass, of course, it will be the same, but for x, y, z, it's like that. Okay, it is very useful in treating problems involving collision, which we'll see soon. Momentum is a vector, and its direction is along v. So vector means it has direction now. Okay, energy has no direction, but momentum is like force, it has direction. Okay, and the direction will point in the same direction as the velocity. Because velocity, we know it has some direction also, correct? The dimension is given by this, and the units is given by this. So remember this definition. Remember this definition. Newton's second law. It is the time rate of change of the momentum of a body is equal in both magnitude and direction to the force imposed on it. And then at that time I say maybe some people don't know momentum yet, right? So we simplify Newton's second law to just F equals to ma. But this is actually the more general form, okay? This is actually the more general form. So second law is actually given by this. F equals to dp over dt. F equals to dp over dt. So rate of change of momentum. So if m is constant, which usually, yes, m should be constant, you can change the equation expression to this form. Okay, so momentum is mv, right? So you can break that down. E become mv, and then mass constant. So we can take it out of this differential. Right? You take it out and put outside. What you're left with on the right is actually your dv over dt, which is dv over dt, right? We know equals to acceleration. All right, we differentiate velocity with acceleration, right? That's why we're going to end up with ma. So you see, force in the end, if the mass is constant, we will get ma. That's why the time we just say force equals to ma is the simplified version. Okay, but F actually equals to dp over dt. Assume that a single force F acts on a particle and that this force varies with time. So this is the formula. If you change it to another form, basically you bring this dp up. Okay, you will get this dp, which is change in momentum, equals to force times dt, change in time. So this is actually saying the change in momentum, delta is change, change in momentum equals to final momentum minus initial momentum. Okay, this is the change, right? It is equals to f dt down here. Okay, so if we have this kind of form, f dt is actually an integral. You integrate from what value to what value, that depends on what you want to find, right? So change in p equals to integral f dt. We have another definition, it's called the impulse. The impulse of a force acting on a particle from time ti to tf, that means the change in time, is given by this. Okay, so this J here refers to impulse. Impulse is just equals to change in momentum. Okay, it's just a definition. Not rate of change of momentum. Impulse simply means the change in momentum, just the change only. So you just take the final minus the initial, you are going to get the impulse. In other words, impulse equals to this expression, okay, integral f dt. So impulse of a force F acting on a particle equals the change in momentum of the particle caused by that force. Just describing this equation. So same thing, impulse is a vector and it has the same dimensions as momentum. Because you see here, impulse is here, right? Down here is just momentum minus momentum. So the dimension confirm has to be the same as momentum. Okay. So then we come to this thing called the impulsive force. Just now we studied impulse, right? Now we come to the impulsive force. If we have a force time diagram, we apply some force over a certain period of time, we are going to get some graph, right? If the graph looks like that in the red one, according to the red one, means we apply this amount of force over this amount of time. The average is actually just the same area as that one. Okay, so average force equals to, you just take average of this. Mathematical part, right? It's just saying you take the area of this, divide by the change in time. That's why you got a 1 over delta t divided by change in time. Basically, the area of it divided by the change in time. But what's more important here is this one. Okay, impulse, the change in momentum, equals to our average force times change in time. Average force times change in time. Impulse approximation assumes that the impulsive force acts for a short time, but is much larger than any other force present. Very little motion takes place during this time, and usually we neglect effects of external forces. This statement is trying to say that for impulsive force, right, this impulse usually happens very short time, like a car crashing into a wall. The time when the car starts crashing, right, to the end of the crash, maybe like in the milliseconds, right? So the change in time is so small that the force involved, right, confirm is much larger than any other external force present. External force could be like wind blowing on the car, yeah, this kind of thing, external force. Okay, so during this period, right, the force usually is so large that we can neglect effects of other forces. Impulse is the same if the area under the FD curves are the same. Is what we have gone through already. The impulsive force is bigger if it acts over a shorter time. For example, a golf ball hit by a golf club. A golf ball is quite hard, right? You get hit by a golf club. The collision, or rather the golf club hitting the golf ball, is not going to last forever because both are very hard, correct? So to illustrate, right, you're going to get something like that. Okay, you apply a force over a very short period of time. Okay? As compared to, it will be smaller if it acts over a longer time. So the same impulse, that means the same change in term, right? If you act over a longer time, the maximum force that you will reach, you realize is much lower, right? This one, the force sustained is so high. This one, the force sustained much lower. Why this example? Because tennis ball is already softer than a golf ball, correct? And then a racket is also much softer than a golf club. So the racket whacking the tennis ball, right? The collision itself will last much longer than a golf club hitting golf ball. So that delta T is much longer. So the force felt by the tennis ball, the racket, right? Max force much lower. So Okay. No questions so far. Then we continue. We come to momentum versus kinetic energy. We already learned about kinetic energy, right? Now we bring in momentum and then see what is the difference. As we know, kinetic energy is half mv squared. Momentum is mv. They are quite similar, right? But actually, they are different things. From this illustration, right, you can see how it's different also. Okay, so consider two ice boats, A and B, of mass m and 2m respectively. So one is mass m, one is 2m. This is heavier. Both are stationary at the start line, subjected to the same force F until they cross the finish line. So start line same, finish line also same, and they are subjected to the same force F. Which ice boat reaches the finish line first? Okay, let's first do part A. Which boat, right, will reach this finish line first? For this question, right, we can compare the acceleration, correct? The acceleration can tell us which one will reach the finish line first. So for acceleration, what is the formula? We use F equals to ma, right? For A, we will then take F divided by m. Same force, so force applied is F, they are both F, but we know the below, right, the denominator, one will be 2m, one will be m. So we can see that the acceleration of A will be 2 times that of, in other words, this small boat, right, will accelerate much faster, which of course quite logical, right? Lighter, so you accelerate faster. So based on this, right, you can already tell TA will be smaller than TB. That means time taken for this one, this boat, this lighter boat to reach the end will be shorter. Okay, so part A, you have gotten the answer. Then for part B, they ask you which ice boat has the higher kinetic energy when it crosses the finish line. We're talking about kinetic energy here. So how do we solve this question? Which ice boat has higher kinetic energy? So if we look at kinetic energy, right, they all start from the same point and they are not moving. So the kinetic energy gain must be the kinetic energy at the end, right, must be the energy gain during this distance. Correct? At the start, it's not moving, zero. Whatever energy at the end is the kinetic energy. So how to compare the kinetic energy? We know the force applied is F. From the energy concept, we know whatever work done by this force, right, will get converted to kinetic energy. Correct? The work supplied by this F into this system will all go into the kinetic energy of this system. So from this, right, we can tell that the kinetic energy at the end will be the same. Why is it the same? Because subject to the same force. What is the work done formula? Same force and then same displacement. So F times the displacement, that will give you the work done, and they both have the same, okay? So they both gain the same energy. That's why at the end, they are going to have the same kinetic energy. Same kinetic energy doesn't mean same speed. It doesn't mean same speed, okay? They have same kinetic energy, but they confirm will have different speed at the end. Okay, part C. Which ice boat has the greater momentum when it crosses the finish line? Now we're talking about momentum. And remember, momentum, the formula, the change in momentum is given by F times D, correct? F dt. And then integrate from 0 to TA. The other one integrate from 0 to TB. 0 is at the start. TB or TA is whatever time at the end, right? Then down here, we're going to compare. We already know TA is smaller than TB, right? So naturally, if they have the same area, this value here will be smaller than this value. Right, which tells us that TA will be smaller value. and P is the momentum, so you get the answer already. Okay. So from the definition of kinetic energy and linear momentum, you can also write down the direct relationship between them. Because you see, they all both have M and V, right? They also have M and V. If you combine them together, you can find some relationship between linear momentum and kinetic energy. And these, they are the relationship. Okay. These are things that you don't have to memorize because it will be too tedious to memorize already. If you really need, right, very easily derive. One you know is half mv squared, the other one you know is mv. Then you just combine them together like simultaneous like that. Okay, but this is the relationship. Now we come to a very important concept, conservation of linear momentum. This is very similar to conservation of energy. It's the same kind of concept. Okay, whatever at the start must be same as the end. But now we're talking about momentum. If there are no external forces acting on the particles, isolated system of particles, means summation of F equals to 0. And since summation of this F, right, is dt over dt, remember Newton's second law is rate of change of momentum, we can write it also in this manner. And because the change is 0, it says that the P, or rather the summation of the P, it must be the same. Constant means is the same. So this, if you rewrite it, it means the starting total momentum must be equal to the final total momentum, since it's a constant, right? That's how we get to this concept. The total momentum of an isolated system at all times equals its initial momentum. Okay, is this statement. I will do this. The total momentum of an isolated system remains constant if there are no external forces present. A convenient way to calculate some parameters, such as final velocities in collisions, without the need to know exact forms of the forces involved. So forces when we learn, right, is useful for calculating certain kind of question. And energy is useful for doing certain kind of problems. Now we come to momentum, right? It will be useful for its own class of kind of questions also. They usually involve collisions. Collisions is when something knock into another thing. Okay, so two particles come together for a short time and they're producing impulsive forces on each other. This is collision. Basically, some two things knock into one another. From Newton's third law, the change in momentum for particle 1 must be equals to minus change in momentum of the other particle. It is from Newton's third law. These are just equivalent statements. Okay, so the both change add up together must be equal to 0, since they will be in opposite direction, correct? So this diagram here, you imagine they are colliding with one another. Of course, draw them far apart is to illustrate the forces acting on one another. But during collision, this is the forces that they will apply to each other. Okay, so for momentum 1, given by this formula, the same formula as just now. And for change in momentum 2, is also given by this formula. Okay, so if you go and look at the force versus time graph, right? If two things collide, the force that they each experience will look something like that. One will go up, the other one will look the same in magnitude, but in the opposite direction. Okay, this is Newton's third law. Okay, so far. Okay, so there are in general two kinds of collisions which we will study now. One is elastic collision, The other one is inelastic collision. So in what's the similarity? In all forms of collision, right? Similarity is momentum is always conserved. No matter what kind of collision it is, right? Momentum must always be conserved. It's like energy like that. Okay, so momentum must always be conserved. But if the total kinetic energy is the same before and after collision, means when they collide, they have some kinetic energy, right? After collision, when they move apart from one another, the energy, kinetic energy, if they are the same the start and after collision, we call this kind of collision elastic collision. Okay, elastic collision. But if the total kinetic energy is not the same, we say it is inelastic collision. So imagine two balls, they knock into each other, right? Two particles, they have some kinetic energy at the start. Then after collision, right, the total kinetic energy they both have is lower than the starting value, lower than the initial value. Then that one is inelastic. As long as it's not the same, it's inelastic. So we first look at elastic collision in 1D. 1D, that means one line, okay? So we are talking about two particles, one with m1, the other with m2, and then they will have their own speeds. Before collision, if they are both traveling to the right, they will look like that. Then after that, they will collide. So obviously, in this particular scenario, for this to collide into this, of course, this has to be moving at a faster speed, right? That's why it will come into contact with this. Then after collision, they will also move away from each other at different speeds. Okay, so because this is elastic collision, elastic, so we can write out equations to represent this collision. One is the conservation of momentum, which will be true for all collisions. Initial momentum, which is m1 v1 plus m2 v2 for the initial state, must be equal to the m1 v1 plus m2 v2 of the final state. Okay, conservation of momentum. Next, because it's elastic collision, it's only for this particular case, because it's elastic collision, elastic. That's why we will have this statement here. Okay, that's why we have this statement here. Remember the definition of elastic. So if it's inelastic, there will be this statement. Okay, energy conservation, kinetic energy. So half mv square of the starting phase must be equals to half mv square final state, okay, of the final phase. Kinetic energy is conserved for elastic collisions. Okay, so for this slide and probably the next two slides, it's quite mathematical. It's to basically find out some characteristics of these collisions. Okay, so now we are at elastic collisions of 1D. We have two equations, right? So the first one is from energy. I'll just briefly go through. I won't go into the specific math. We won't test you on the derivation or solar anyway. So this is from the energy conservation. You go and move things around and make it go to this form. Okay, make it go to this form. Shift things around, make it go to this form. Call it equation 1. Equation 2, from the conservation of momentum equation, as you can see, mv is momentum, right? These are our mv. So if you go and shift things around and make it go into this form, we call it equation 2. We make them go into this form, right? So that we can take 1 divided by 2. We want many things to cancel out. That's why we smartly make it these forms. Okay, so in the end, you are going to get this statement here, which if you rearrange it, right, you're going to get V1I minus V2I equals to V2F minus V1F. This means approach speed. As you can see, V1I minus V2I, this is the approach speed. Means the speed at which this approaching, at which one approach to their relative speed line, in other words, will be equals to the speed of separation. Okay, so the relative speed here will be equals to the relative speed here, but now they are separating. Right? Makes a bit of sense, right? You all got play billiard, you all got play pool. If you all got play pool or billiard, right, this momentum concept, right, will be more natural for you. Okay, because pool and billiard is one of the closest things around us that can get uh, to elastic collision. It exhibits this kind of traits very well. So in this case, you can keep hitting a ball and then they collide, right? And then what happens after? To find final velocities in terms of initial velocities, we are still at the same thing, elastic collisions. So we perform all mathematical operations. Okay, so this is the expression from just now, right at the end. We make V2F the subject, then we substitute this momentum equation. Okay, this is the momentum equation, this one. Okay, then if you work it out, you make V1F the subject and also make V2F the subject. Because in this slide, right, our aim is to find the final velocities in terms of both initial velocity. Okay, so it can be done. That means you are describing the final velocity. That means after collision, after collision, you are describing that in terms of their initial velocities. Here they are all I. Right? Okay, then some more traits that we can pick out from this thing. So these are the two equations, V1F, V2F. So we can break it down into more cases, right? So case one, if M1 equals to M2, that means these two balls are, imagine they are the same ball, same mass, everything same. Okay, so if they collide into one another, right, and you substitute M1 equals to M2, you can imagine all these M1 minus M2, all these will get cancelled out, correct? Because they are the same. Okay, so in the end, you're going to get something very simple. V1F equals to V2I, and V2F will be equals to V1I. You see these two expressions, right? It actually means the particles exchange velocities. The particles exchange velocity. Okay, and this is something that you will observe. You go and take two billiard balls hitting onto one another. After collision, they will exchange velocity. Okay. And case two, if M2 is initially at rest, that means this M2, let's say is not moving. So now M1 is coming to collide into M2, which is not moving. So we will substitute V2I as 0 into these equations here at the top. Then you will get another two smaller equations because now we have another, coming to another more specific case, right, where M2 is not moving. So if M1 is much greater than M2, so now imagine M1 is a large metal ball, very heavy one. Okay, come and collide into a very small plastic ball that is not moving. What will happen? Okay, this will happen. V1F will be roughly equals to V1I. So you see, the final velocity of 1 will be roughly equals to the initial velocity of 1. In other words, because this ball is so heavy, right? This is so light, right? It almost has no effect on this at all. It will just continue at the speed. Okay. And then what happens to the other ball? V2F equals to roughly 2 times V1I. So this will start to move off at a velocity that is twice that of particle 1. Okay, so that's the phenomenon. And then what if M2 is much bigger than M1 instead? Now M2 is still at rest. M2 is still at rest. M1 come and bang to M2. So now M2, right? Imagine this is a very large metal ball, very heavy one. It's not moving. Then M1 is a ball like ping pong ball, plastic one. Come and knock into this heavy ball. What will happen? Okay, this is what will happen. V1F will be roughly equals to minus V1I. What this says, right, is 1 will almost get reflected back. You see minus, okay, which makes sense, right? Because this is so heavy, it's like a wall already. This ball come and bang into this very heavy ball, it will just get reflected. Okay, then V2F is almost zero because this is so light, bang into something heavy, right? Almost has no effect. So V2F will be nearly zero. Okay, the scenarios that I described, if you think of it in real life, right, it's like common sense, lah. But mathematically, this is how we describe them. Okay, transfer of kinetic energy during collision. Transfer of kinetic energy. So when collision happens, right, you can also expect energy to be transferred. Something that is moving, not into another thing. Then maybe this one stop, then the other one go on. There is a transfer of energy, right? Transfer to the next particle already and then go somewhere else. That's the transfer. So how to find the transfer in energy? For example, I'll use this one. We talk about kinetic energy, right? That's why half mv square will come into the okay, half mv square will come into the so basically half mv square, then the v square, right? You substitute this v2f inside. This is what you will get. Okay, then if you go and simplify it, you will have different scenarios also. What if m2 is much bigger than m1? What if m1 is much bigger than m2? You're going to get different kind of transfers. But the maximum transfer will occur when they have the same mass. Okay, so that's our elastic collision. Now we come to inelastic collision, and at the most extreme case of inelastic collision, right? Remember, in general, inelastic collision means momentum conserved, but kinetic energy is not conserved, right? At the most extreme end of inelastic collision, the most extreme scenario, we call it the perfectly inelastic collision. What happens here is before collision, they look like that, right? Look the same. After collision, two particles, right, they stick together. Okay, when they stick together and then move off as one object, right, like one particle like that with the same velocity. If this happens, we call it perfectly inelastic collision, or rather totally inelastic collision. It has different names, but referring to the same thing. Okay, so the momentum conservation will be in this form. Don't need to memorize also because you see, you know collision means there will be momentum conservation, right? Then you will try to write it out. So how you write out? The momentum at the start, which is m1 v1i down here, plus m2 v2i, because you need to account for both, right? Must be equals to the momentum at the end. Then you ask yourself, at the momentum at the end, what do you have? You have m1, m2 as a huge mass on its own, right? So you write m1 plus m2 times the velocity of this whole huge mass, right? That's why you have mv here. In the end, you already have your momentum conservation already. Okay, so there's no need to memorize like, oh, for perfectly inelastic, it will look like that. You don't need to memorize. Just know the main concept. You will write out for any particular areas already. Okay, the one in the red box here is just make VF the subject. And then we come to this term called the coefficient of restitution. Basically, it's just another definition. Okay, so what is this coefficient of restitution? It's defined by this. Okay, so E equals to relative speed of separation divided by relative speed of approach. Okay, so if you write it out in maths, it will look like this: V2F minus V1F divided by V1I minus V2I. Okay, so just now remember during elastic part, right? We say the relative speed of separation equals to the relative speed of approach, correct? That's why in elastic collision, right, you're going to get this coefficient of restitution equals to 1. Because top equals to bottom, right? So you're going to get 1. Anything inelastic, right, you are going to get less than 1. relative speed of separation will be less than the relative speed of approach. Okay, you can also imagine it as when the collision happens, right? Energy is lost to somewhere, not in the particles anymore. So when the energy is somehow lost, a bit of energy is lost, right? The speed at which they separate from each other will be smaller than the speed of approach, really, correct? Because energy is lost. So smaller than one. Of course, the most extreme end, when they stick together, there is no more separation, right? So it's zero. Okay, so basically it's zero, smaller than one, and one. And then in some special case, you'll get some values more than one. How is that possible? How can two things collide, then the relative speed of separation becomes so high? It can only happen when there is energy gain into the system. So if you have something collide, right, then in that system, there is energy injected into these particles to give them a lot of energy such that the particles shoot away from each other, right, at a much higher speed. Okay, this can happen usually during explosions. Okay, during explosions. If this one collide with this one, then at the collision, right, explosion occur. Okay, the explosion release a lot of energy which goes into the system, the mechanical and energy of these two particles. Accelerate them away, so come very fast. Okay, grenade also work the same way. A grenade, you throw a grenade, right? Actually, you throw it. Then after that, explosion happens, right? That's why the ball bearings inside, there are many ball bearings, there are many bearings inside. They start to move away from each other so fast because energy is released to increase their mechanical energy of the. Okay, so it's possible to be more than one. Okay, just a simple example which don't even have any words. So this scenario is you have M1, M2, and H given. Find V1I. So what is this scenario? Imagine you have a block hanging down. You have a bullet flying towards the block. Okay, hit the block and then stay inside. What will happen to this block? Because it's attached to the top, it's going to swing like a pendulum, correct? It's going to swing like a pendulum upwards. Down here, it's going to swing like a pendulum. So when this bullet collide with the block, this system here, we are going to have the conservation of linear momentum. Okay, because it gets stuck together, so we are going to have M1 plus M2 times VF to M1 V1I. Actually, this is already a shortcut to make VF the subject. Initially, if we write out the conservation of momentum for this collision, it should look like that. Okay, M1 V1I equals to M1 plus M2 VF, like this. Okay, basically, it's the same thing. Okay, but this, the one that I wrote out, right? This is the general form that you will be writing out if you meet this kind of scenario. Okay, because it's a collision. So M1 plus M2 right down here and VF is right after the collision. So the block hasn't moved up yet. So this one, right, we are describing just still here. It's like right after the collision. The block hasn't moved yet. Okay, right at that moment. It's given by this. And then we have the next scenario, which is when the block moves up. Okay, when the block moves up, we can write out conservation of mechanical energy already. Because now the block is down here, the block with the bullet is down here, right? It will start to move off at a certain velocity. Means at this point, at the lower point, it has kinetic energy, correct? It has kinetic energy, and now it's traveling upwards. So all this kinetic energy, as it moves up, must all be converted to potential energy. Okay? Kinetic energy, half mv square, all gets converted to potential energy. That's how we write out this equation over here. Okay, then if you combine the two equations, that depends on what you need to find. In this case, V1I. So combine them both and then find V1I. Of course, this question has no numbers. That's why everything is still in letters. Okay. Yeah, so that is 1D collision. How about 2D collisions? Okay, how about 2D collisions? So, like many other topics, after we study, we move into 2D and 3D, right? So, fortunately, 2D here, right, works about the same as how we would do our kinematics and forces. Okay, basically, for 2D, we will have two direction, and we can write out the conservation of momentum in both directions separately, independently. Okay, so if you write out for the x direction, everything will look the same, just that everything you will use whatever that is in the x direction. Same thing for the y direction, conservation of momentum will hold, but all these values are m1, all these v1, v2, all these are they are for the y direction only. Okay, momentum in each direction is conserved. For elastic glancing collision or oblique, that means you strike a particle. You see, this particle strike this one, but they never collide head on. So what will happen? They never collide head on. That means they will go away from each other, not so nicely anymore, right? They will hit like this, and then M1 will go somewhere to the top right, M2 will go somewhere bottom right. This is called glancing or oblique collision, opposite from head on. So if this happens, right, it naturally becomes a 2D collision. You see, if you go head on, they go away in the same direction, that's 1D. But at any other angles, right, if you don't collide head on, you will always end up in a 2D collision really. Okay, so you can write out two different equations, one for each direction. So the top one here is conservation of momentum in the horizontal direction. Okay, top one here is for horizontal. This is for vertical. Yeah, so you see, so for horizontal, we ask ourselves, at the start, right, what do we have? We only have M1 V1I, which is nicely in the horizontal direction. That's why it's down here. And M2 is not moving. That's why it's not here. All right. They must be equals to the momentum of the final two add up together. And then we look at this M1. What is the horizontal component? It will be this M1 V1F traveling at some funny angle, right? We only want to resolve this into the horizontal direction. So what do we do? It will become V1F cosine theta. That's why cosine theta appear here. Okay, basically, we are finding the component for the horizontal part only. Okay, for the horizontal part only. Then the other mass, don't forget, is also there. It's still moving. Not still moving. It moves after the collision, right? So when it moves, you have momentum. So you have M2V2F. Now you only must account for the horizontal direction. That's why you put a cosine phi. Okay, that's for the horizontal direction. Then for the vertical direction, you also write out another momentum conservation equation. At the start, you see one is moving to the right, one is not moving. So in the y direction, you ask yourself what do you have? Nothing is moving up or down, right? So it will be zero. Okay, it will be zero down here. Then at the end, you will just need to resolve this to the vertical component. And take note down here is negative because they are moving away different directions, right? One is moving up, one is moving down. We're looking at vertical directions only. So one is moving up, one is moving down. Okay, so those are the two equations that we will have. And then because it's elastic, right? Remember elastic is actually a keyword. When it's elastic, we can always write out this conservation of kinetic energy. If it's inelastic, right, then no such statement. Okay. So in the same scenario, right, if M1 equals to M2, that means they have the same mass. This will occur. Okay, so conservation of momentum. Just now we have M1, M2 inside, right? All will disappear because they all cancel out. Now we assume they have the same mass. something like that, which in vector form, it will look like that. Okay, V1I equals to V1F plus V2F. They are all vectors, right? So you can draw them out. Vector diagram. And then for the conservation of kinetic energy, right? You take away all the m because now they are the same. It will give you this V1I square equals to V1F square plus V2F square. You look at this. This is very familiar, right? It's actually our Pythagoras theorem. All right. So what does it say? It says that this must be a right angle lah, because Pythagoras theorem is true here. Right? That means this must be a right angle. So theta plus phi must be 90 degrees. Okay, so if you have this colliding into this one, right? Theta plus phi, it will be a right angle. Okay. And now coming back to our billet, you know why professionals, they know when they hit the ball, right? They know where the other ball will travel. Because of this, it will almost be a right angle because the cue ball, all the balls are they are roughly the same mass. Okay, almost exactly the same. The white ball that you hit, right, is only very, very, very slightly heavier than the other balls. Okay, cannot feel one. You hold in both hands, you'll never tell. Okay, almost exactly the same. That's why when they hit, right, they will travel almost in right angles. This is assumed you hit in the middle of the ball, like you don't add curve, you don't add sliding here and there. Okay, it will result in this manner. Okay, so this is when both M they are the same. Okay, now we come to an example which I believe is towards the end of the notes reading. Okay, so after this we'll take some. This example, which is a very typical example for 2D collision, a 950 kg car traveling east collides at an intersection with a 1900 kg pickup traveling north. The two vehicles stick together as a result of the collision, and immediately after the collision, the wreckage is sliding at 60 meters per second in a direction 24 degrees east of north. So basically, whatever described here, right, is illustrated here. They one to the right, one traveling up, and they crash, and they stick together, and then both move in this direction. Calculate the speed of each vehicle before the collision. So this is a 2D collision, right? As you can see, you have somewhere to the left and right, you also have up and down. So it's a 2D collision. So using the conservation of linear momentum, you write out in the x direction first. So in the x direction, you look at what you have. You have only the car. So MV for the car must be equals, okay, the pickup truck is not appearing here, right? Because it's traveling up and down, okay? This pickup truck is not traveling left or right. So in the x direction, that will not appear at the initial. Then at the right, you must go and find out what momentum you have along the x direction. So you need to add up the both mass because momentum is mv, right? Now the wreckage is stick together and move here. So m, which is the mc plus mt, multiplied by the v, but this v you have to resolve to become the x direction, which is sine theta. Okay, which is sine theta. Theta is 24. Theta is 24, so sine theta is here, right? Opposite. Sine theta is here. Okay, so you go and substitute all the values inside. You realize, oh, actually, by taking the x direction, you can already find the initial velocity of the car already. So we are 19.5 meters per second. In the y direction, exactly the same thing. Now you go and look at momentum in the y direction. Car is not involved anymore because they are left and right. Now you only have pickup and then the same thing on the right, but now you must resolve into the vertical direction. That's why just now sine right now is cosine. Okay, then after this, sub in all the values, you will get velocity of the pickup. Okay. Okay, then after that, all these supplementary questions, just read and then read the solutions also. Like, it'll be very, very helpful. Okay, all these supplementary questions. So that one you will do on your own, and then if you have anything, you can come. Okay, so maybe now we take a longer break. We come back at say 8:50. Okay, 8:50 we start the second part, and hopefully can end earlier again lah. Okay, because the past two lectures actually never end much earlier lah. Okay, so hope today can end earlier. Okay, so see you all at 8:50. Oh, anyway, stay in the chat. Again, stay in the chat because I'll mark attendance based on whoever that's in this chat room. Okay, don't need the QR code anymore. So I will just straight away mark. I see whoever is in this chat room, right? I'll mark you as present. Okay, so stay in this chat room using your devices. Okay, thank you. See you all at 8:50. Okay, hello everyone. Welcome back. So I hope you all had a good break. Now more refreshed already, right? Let's go through the next part of momentum and collisions. Not exactly really about momentum and collisions, lah, okay, but on something that is still related. Anyway, today maybe let's end earlier, lah, okay? Confirm can end earlier. 9 plus should be able to end already. Okay. But for those who have questions, they can ask me, like I can be here. Okay, so let's start. A mechanical system moves as if all its mass were concentrated at the center of mass. So now we come to this new concept, center of mass, CM. If an external force F acts on this system of total mass M, the CM accelerates at A equals to F over M. So following F equals to MA, right? A will accelerate at force divided by the total mass. If an external force Fx on the total mass M. This is independent of other motion, for example, vibration and rotation of the system. Provides another way to look at the conservation of linear momentum. Okay, so now that we look at these statements, right, maybe still a bit blur, okay, not so clear, but later we will see how this concept is applied. So first we need to find out what exactly is CM first, okay, center of mass. Again, in 1D, that means one direction, how do we find the CM of particles? So let's say we have just two particles, two only, which is the easiest. So let's say M1 is here, the distance x1 from 0, from this y-axis, right? And M2 is at the distance x2 from this y-axis. So to find the center of mass for these two particles, right, where is the center? We'll be using this formula. Okay, so we take mass of 1 times the distance of 1 from the same reference point. It must be from a reference point. Later, second particle and the third, fourth, so on, right? You all must use the same reference point, then it will be correct. Okay, so in this case, M1x1 plus M2x2, again, same reference point. Divide the whole thing by the total mass. Okay, basically you sum up each of them individually, then divide by the total mass to find sort of what is the average distance away from the reference point. Okay, in this way, right, you will get the center of mass. Okay, so that's how we find the center of mass. If we want to find the CM of the sheet, and we use the CMs of the different colored sections to find the CM of the system. So imagine we have this system over here. We have different blocks, right? 1, 2, 3, 4, 5, 6. 6 different blocks actually. But let's say if you group them up into two each. So you group the top two together, and these two together, and these two together. You will have different CMs, right? Now you have different CMs. So if you use these versus you group them differently again, and then calculate the resultant CM, the final CM, will they come to the same exact point? Okay, that's what we are trying to find out. Okay, so for example, for this, if you group them up like this, right? The intermediate step, they are going to have like different CM. So you see, I'm drawing on the second image now. Okay, so the CM will be something like this, right? And now it's as if you take these 3 CM and then combine them together to find another CM. What is the resultant? Then the last image, it will be something like that. This one is here, this one is here, this one is here. Will they all come to the same point? Okay, so the answer is yes, lah, right? So answer is yes, but why? This is the explanation. Consider any first two masses M1 and M2. So to find the XCM of that, right, is this standard formula. Okay. So now we have XCM of 1 and 2. And now we add the third mass, M3. We treat the mass 1 and 2 as one single mass. So now after we combine M2, right? We have a new CM and then this combined mass. Now we bring in the third one, okay, which means we have M3 and then M1 and M2 is a single mass already. So in the end, we still have two. So apply back to the same equation, apply back to the same equation, and in the end, right, you'll find this. M1x1 plus M2x2 plus M3x3 divided by their total mass will give you the XCM. So it's exactly the same. Okay, no matter how you separate them. If you do combine 1 and 2, then you find 3, or you combine 2 and 3, then you find 1. It will all give you the same CM at the final. I mean, a final answer. This is the same as finding CM of 3 masses directly. By induction, you will apply to any number of masses, and we can divide the system into any convenient shapes combinations. Okay, so this is how we find center of mass for ships. So just for example, we use this for example. The 3 colored sections have equal mass, say M. So let's say they all have equal mass. By symmetry, the CM of the sections will be this. The CM for block 1 will be at 10I plus 25J. 10I is here, 25J is also here. Okay? Then CM of 2, it will be somewhere here, right? Somewhere here. 5I plus 10J. And for 3, same thing, just in the middle, there will be 20I plus 5J. So you combine them using the formula to find a CM. In this case, it's 2D, right? So you will do one in the X direction and then do the other one in the Y direction. Basically, when you do one for X, right, that means you go and find the XCM. Use the M1, then put the distance in the X direction for that one, which is 10 down here, right? Then 5 is from here. 20 is from here. Okay, basically, this is for X direction only. Okay, if you do this, you're going to find the X coordinate of the CM. Then you do the exact same thing, but now in Y coordinate. You're going to get another value. So these coordinates, right, will be the XCM of this entire shape. Okay, so 11.7 will be the X, 13.3 will be the Y. If you want to plot out for this one, the XCM will be somewhere around here, right? 11 and 13, somewhere around here. Okay. So that's just 2 or 3 particles, right? How about for a system of particles? That means we extend the concept to many particles. Now we have many hundreds, thousands of particles. How to find the XCM? Actually, it's the same. You sum them up together, all the M times X numerator, you plus together, summation, divide by their total mass. Okay, same thing. You do one for the X direction, you do one for the Y direction, you do one for the Z direction. So to rewrite it in vector form, right? R is our position vector. It will look like this. Okay, so the general formula will be RCM, position vector. So the CM will be MR. R will have all 3 directions. This is just a position vector. So inside R, right, we have I, J, and K. Basically, M times that, and you divide by the total number of mass. So imagine you have many particles, okay? So that's how you find the CM of this system of particles. Okay? So that's for system of particles. How about for an extended object? Extended object is the same. That's why we learn about system of particles first. Extended object means an object with many, many points, correct? So imagine this is the object, this one. It's not a point anymore. So this object, there are many, many particles on it. They are stuck together, but there are many, many particles. Okay, so in the end, it's still the same as system of particles. Okay, to find the CM of this object, right, it's just summing all the mx and my, mz of all the particles, then divide by the total mass. Okay, this one shown here is for the x direction. So same thing, summation of mx divided by total m. Okay, then same thing. You have many together, right? So you will do an integration to sum them up together. So you'll get the equations that look like that. In the x, you have 1. In the y, you also have 1. The z, you also have 1. So this one is the general formula to find Cm. Okay, so this is where the Cm is. It's given by 1 over total mass integral of r dm. R is our distance, or the displacement from a reference point. It can have x, y, and z direction inside. Okay, and dm is just a very small mass. Some characteristics of Cm for homogeneous. When we say homogeneous, that means constant density throughout. For homogeneous body that has a geometric center, the Cm is the geometric center. So, for example, like solid sphere, tube, and cylinder, right? The exact middle point, the geometric center, will be where the Cm is if it is homogeneous. That means the whole object, right, is exactly the same density. On the left, on the top, on the right, on the bottom, anywhere, right? It's all same density. Of course, in real life, this is not talking about ideal situation. In real life, even objects that seem like they are homogeneous, right, they may not be. Even if you now hold an iron rod in hand, right, or steel bar, right, look the same, right? The left also steel, right also steel. A steel bar may not have homogeneous density. I'm talking about real life because during the manufacturing process, it may not be so ideal. They may have different the particles may have different arrangements along different parts of the bar. So in that sense, right, if density is slightly different, then the object may not be homogeneous anymore. That means the Cm may not be at the geometric center, maybe slightly off, depends on how off this density is. Okay, center of mass of any symmetric object lies on an axis of symmetry and on any plane of symmetry. That means for symmetric object, the Cm confirm will lie along the symmetry, which is of course common sense but it's one of the characteristics. So if we have a triangle, let's say it's an equal triangle, right? The Cm will lie along this line. Okay, so somewhere along this line, will be the Cm. If you have a circle, somewhere along the middle, okay, of course you know it's in the middle lah. If we have a square, somewhere along the symmetry, okay, so that's what that point is talking about. Third point, if G is constant over the mass distribution, the center of gravity coincides with the center of mass. If an object is hung freely from any point, the vertical line through this point must pass through the center of mass. So generally, we assume G is constant over the mass distribution because we are so small, right? For example, your screen in front of you now, the left side of the screen and the right side of the screen, they experience the same gravitational acceleration, right? It's all 9.8. That's why the CG will be the CM. Okay, CG is center of gravity, CM is center of mass. So if they are the same, you hang something, if you hang something, right, gravity will act, right? If an object is hung freely from any point, the vertical line must pass through the center of mass. What does this mean? So let's say any object, a random object, let's say random object like that. If you go and pin it on the wall, you go and pin it on the wall here, this is a pin. And then the object finally rests at this position, right? It means if you draw a vertical line through the pin, my hand is not resting on the table, so a bit off. So if you draw a vertical line down, right, these are points where the CM must lie, okay? Must be on the vertical line. Okay, same if you have some other random shape or what. If you hang a pin here, vertical line down, must also be along this line, okay? That's what it's trying to say. Fourth point, CM needs not be within the body itself. Okay, because some objects can be quite weird shape, right? So the CM may be out of the object. Like just now the sheet that we see, the CM is actually outside the sheet, right? So if you have a boomerang kind of object, let's say something like that, if you hang here, you will stay in this position, right? You draw a vertical line down, the CM maybe is here. Okay, that's a CM. Maybe it's out of the object. Okay, maybe it's out of the object. That's what the fourth point is talking about. Okay. So some examples of how to find CM of different shapes. We will use the general formula to find the CM. So an object of mass m is in the shape of a right angle triangle whose dimensions are shown in the figure. Locate the coordinates of CM, assuming the object has uniform mass per unit area. So this is a triangle, right? And it's 2D only. So we have y direction, we also have x direction. So XCM general formula, YCM general formula. We'll be using these formulas, these general formulas, to find the XCM. So these are just examples of how we're going to find it. So given an object like this, we would want to chop up the triangle into many strips, correct? So before we chop them up, actually we should write out all the dimensions first. So the distance from 0 to this chop strip, namely x, and the whole thing is a. The whole height is b. From this, right, we can write y in terms of b, a, and x, because we know from proportionality, right, if we take y over x, y is this one, and then x is this one. Y over x equals to b over a. Okay, proportionality. Then make y the subject, it will look like that. Then if you chop up the strip, the height is y. The x for the very, very thin strip, we will call it dx. That means a very small change in x. Okay, we get ready all this is to put into this general formula. Because the general formula is 1 over m integral of x dm, right? So the total mass, we can also know that is this expression. But down here, the rho, this is mass per unit area. Okay, mass per unit area. How to find the total mass? We take mass per unit area times the area. The area of a triangle is half AB, correct? Half times base times height. So mass per unit area times area, we are going to get the mass. Usually the rho stands for volume, but this one is a 2D question. So rho here becomes mass per unit area. Okay, and this one you move things around, you make rho the subject. Okay, so that's for big M. For the small m, right, which is the mass of this very small strip, okay, which is the mass of this very small strip, we can also find an expression for it. Because again, mass equals to rho, mass per unit area, right, times the area. What's the area of this small strip? Basically just your y times your dx, right? That's why it's here. And then from here, we can start to put other information inside already. Just now we found that y equals to b over ax, right? Found that y equals to b over ax. This whole thing we can throw inside here. Okay, that's how we get that this equation here. So now we can apply the general formula to find the XCM. So XCM general formula given by this, right? Is the general formula. So now we know dm can be substituted with this entire thing here. All right. And then we also know this rho inside can be substituted with this one. Okay, that's why you will go and change. That's why this dm disappear, become something dx, because you sub this inside. And then this rho, right, you substitute this inside. Okay, basically after that, you will just go and solve do integration, solve from 0 to a, because you want to solve from 0 a. Now we are talking about x direction, right? So 0 to a. So you solve, you will get xcm equals to 2/3 a. Okay, xcm equals to 2/3 a. So a is from 0 to this point, right? It's telling you that xcm, right, will lie along this line, somewhere around here, 2/3. Okay, 2/3, I assume is around here. Okay, maybe around here. Okay, because this whole thing is a, right? So 2/3 is around there. Okay, does it ring a bell? Because in upper primary or lower secondary, right, we are always told that the center of the triangle is 2/3 on the base and 2/3 of the height, right? So it's somewhere around here. But this is the way mathematically to find that cm. Okay, is 2. Then same thing lah. For y direction, right, you will chop up the slice in a different manner because just now we do x, correct? So now we will do y. We chop up this manner. Again, from proportionality, we're going to get this. And this is still A, this is still B. But because now we are doing from the top to the bottom, right? Small strip all the way to the bottom big strip, we would want to write out the length in terms of x. We cannot just straight away use x really. X starts from 0 point, right? But now we are starting from the other end. So what do? We will define this length as a minus x. A is the whole thing, right? X is 0 to wherever the point is. So this length must be a minus x. Okay, this is the only difference. The other parts, right? How to get this dm, all this, exactly the same. Okay, so you're going to do integration, substitute the values inside, do integration. In the end, you will find that it's 1/3 b. That's where the ycm is. And then you go and see 1/3 b is around here, right? So yeah, x is 1/3 from this end, right? Then x is y is 1/3 from this end. So the cm of this, right, is somewhere around here. Okay, so mathematically, this is how we find our center of mass. Okay, so that's for triangle. Let's look at for a cone. How do we find the cm of a cone? So same thing lah. We will draw out the diagram. This is in 3D already, but fortunately, right, it's symmetrical. Along the, we only need to care about one direction, okay, which is along the z direction. This is changing, right? For x and y direction from the middle, obviously there's nothing to calculate because x and y direction where the cm lies obviously along the center. Okay, so there's nothing to calculate for x and y. We only need to care about the z direction. So same thing, draw out this diagram. The total radius here is capital R. If we chop it up into slices, right, of this volume, the slice radius will be small r, and then this small height, right, we'll call it dz. Okay, and then from the bottom to wherever the slice is, that is our z. To calculate the mass of this slice, dm means change in mass, right, of this slice. So dm, which is the mass of this slice, given by rho. Rho now is our mass per unit volume really. This is in BD. Okay, mass per unit volume. Take rho times volume. How do you find the volume of this slice here? This pizza here, how do you find? You take pi r square, which is the surface area, times dz. That's the volume this slice, right? Of this small slice. Okay, so rho times volume. Okay, then this basically why it becomes like that, right? This small r, they use this proportionality to write it in terms of the total height and the total radius, because this is more universal. Okay, then total mass You just sum up all the mass together, which is from 0 to h. You get this. So you find an expression for the total mass also. Now we are ready to apply the general formula for center of mass. This is how we do it. You substitute whatever you have found before, which is dm already know, right? dm already know. Actually, m also know, also known. But this step they haven't put in. So they put in here first, and then they perform the integration. It's a simple integration. You have z here, you have z square here. Actually, it's z cube. Okay. Integration, that means you raise it to the power of 1, then divide by 4. Then you are going to get this. And this is where they sub the m expression inside. Okay, so all these, they are all going to cancel out, disappear. And then what's left is zcm equals to 3/4 h. That means zcm, the center of mass for this cone, right, will be at 3/4 of h. So somewhere around here. Okay, 3/4 of h. Then xcm, ycm, the one don't need to calculate. Obviously, it will be at the z-axis itself. For both 0. Okay, so that's how we calculate center of mass. Now we come to a motion of system of particles. Motion of a system of particles. Why we learn CM, right, is for this purpose. We want to look at the motion of a system of particles. So this RCM, this is how we get a CM, right? It's given by this. How do we get the velocity of the center of mass? Let's say this whole thing is moving. We differentiate this. Remember, position, differentiate, become velocity. Okay, then this R, we can write in terms of this. So we substitute this inside here. And then take out a capital M, it will look like this. So velocity of the CM will be summation of mv for each particle divided by the total mass. Then if you move this capital M, right, over to the left side, down here, you'll get mv equals to summation of mivi. So it's the total momentum. Okay, mv is the momentum, so this is the total momentum. What this means, right, is the total linear momentum of the system is equal to that of a single particle of mass m moving with velocity cm. Okay, now maybe a bit confusing, right? Later example will be clearer. Basically, you have a lot of particles, right? There will be a cm, correct? At any point of time, there will be a cm of that, a lot of particles. Then this cm, right, the speed, right? If you take the total mass times the cm, the speed, right, is actually equal to all their momentum, the same, okay? Then we move to another observation. We continue. To get acceleration, we differentiate velocity. Okay, so we're going to get this. This is the acceleration of the cm. And then in the same manner, you're going to get ma. This is acceleration of the cm. Must be equals to the summation of forces acting on it. Okay, you're going to get summation of external forces equals to ma. And we know this force, right, equals to rate of change of momentum. These equations now sound a bit confusing, but actually this is what it means, this sentence here. The cm moves like an imaginary particle of mass m under the influence of the external resultant force on the system. So all these many particles, right, it seems like it's only moving based on the center of mass of all of them. Okay, so one of the simplest illustration of that thing, right, is this projectile, exploding projectile. So a projectile fired into the air suddenly explodes into two or more fragments. What can be said about the motion of the center of mass of the system made out of all the fragments after the explosion? Imagine you fire a shell, tank, fire a shell, the shell explode, right? But for this simple case, we just assume only explode become two pieces, lah, okay? Two pieces. After the shell explodes, the two fragments follow individual trajectories, their own trajectories, but the center of mass continues to follow the shell's original trajectory. So if it explodes, this one will have a new trajectory, correct? A new trajectory. Then the other piece also have its own trajectory. But at any point, you see this is the first instance. One is here, one is here, right? What is the CM in between the two of them? Then the next instant, one is here, one is here. The CM is in between the two of them, and so on. Okay. So at any point of time, the two particles, there will be a CM in between, right? The two of them. So you see here, this is the original trajectory, correct? If this shell never explode, it will follow along this line. Okay, if the shell never explode, it will follow along this line. And this is where the CM will follow, okay? So it follows the line as if it never explode, okay? Because the CM of the system of particles will still follow as if it's one particle, which is where the CM is. Okay, so now it's for two particles only lah. But imagine this shell explode into 100 particles flying all over, a lot of 100 particles, right? At any point of time, the 100 particles, you can sum up that CM, right? The CM will be following the original trajectory of the projectile motion. Okay, so this illustrates what the previous two slides is talking about. So now let's look at one example. Shell exploding in mid-air. A 12 kg shell launched at an angle of 55 degrees above the horizontal with an initial speed of 150 meters per second. When it is at its highest point, the shell exploded into two fragments, one 3 times as heavy as the other. The two fragments reached the ground at the same time. Assume that air resistance can be ignored. If the heavy fragment lands back at the same point from which the shell was launched, that's the criteria. Where will the lighter fragment land and how much energy was released in the explosion? So you can draw a simple diagram to show. You fire from this point. This is the starting point. You fire. When it reaches the highest point, it explodes. Then the heavier shell, right, follow the original one back to the original spot. Then the lighter one, of course, will fly further somewhere, right? Lighter fragment. So you'll reach this point X2. Then why there's this dotted line here? This dotted line is the trajectory if this shell didn't explode. Okay, so if this shell never explode, right, it would have traveled in this projectile motion, this trajectory. Okay, with this diagram, we can start to solve the problem. The velocity at the top of the flight before explosion is given by this. Okay, because it's fired 150, right? Wait, I write up. Okay, so fired down here, fired 150 meters per second. And then this angle, right? Angle is supposed to be 55 degrees. Not very well illustrated, but okay, it's 55 degrees. So we know this is 150, we know this is 55. We can find the horizontal component, right? We can resolve the horizontal component. And the horizontal component is 150 cosine 55. Correct? 150 cosine 55. That is the horizontal component. And remember, for our projectile motion, the horizontal speed won't change, right? Remember, we assume that the horizontal velocity stays the same throughout. That's why at this point, at the highest point where it's traveling only to the right, correct? Not traveling up or down, it's traveling only to the right. The V naught must be equals to the Vx. Or rather, the velocity here, right, must be equals to the horizontal velocity, given by 86 meters. Okay? Then we can use the fact that CM travels along the original parabola to find where the lighter fragment will land. To find the CM, to find where the CM will land, we first need to find the time to reach the top. So from here, you fire up how long you take to reach the top. Kinematic problem. So we will use kinematic equations to solve this. This is from V equals to U plus AT. Okay, V equals to U plus AT. Upward Y positive. That's why A will change to minus G. And we want to find the time to reach the top, right? That's why we will substitute velocity in the Y direction equals to 0. At this point, at the highest point, there is no Y velocity, okay, because it comes to a stop before going back down. So we find that time taken is 12.5 seconds to reach the top. Correct? Then we will know that the time taken to come back down, right, will be exactly the same. So time to go up will be 12.5 seconds. Time to come back down will also be 12.5 seconds. This is how we find where the XCM is. We already know the horizontal speed. We just need the time, right? We need the time to find the XCM. Speed times time give you distance. So we know the total time taken will be 2 times 12.5 because you go up and come down, right? You go up and come down. So 2 times 12.5. That's what you'll do. 2 times 12.5 and times the velocity. Okay, this horizontal velocity, which we have already calculated here. That will give you XCM at 2150. Okay, so now we're coming closer to the answer already. We know this XCM is 2150. We know this is at 0 position. We can use the CM concept to find where x2 is, correct? Basically using this formula. XCM must be M1 x1. X1 is 0, that's why 0 here. Plus M2 x2. We know the mass, one is 3 times the other. Okay, total is 12 kg, so they must be 9 and 3. Then divide by the total mass. We are going to get x2 equals to 8,600. Okay. And the other part, they ask you how much energy was released in the explosion. How much energy is released in the explosion? So you need to go and find out the velocities, right, of these shells. So since the 9 kg fragment landed back at the original position, ouch, because only this question will happen. In real life, you fire a shell, how can the heavier part come back to you and hit yourself, right? But for this question, the heavier part come back and hit yourself. Its velocity must be negative that of the shell. So you go up, right, explode and come back down. So the velocity must be exactly negative with the same magnitude. Okay, then now we can use the conservation of momentum to find what is the velocity of the lighter fragment. Okay, starting before explosion, we have both masses together, which is 12 kg times the velocity at that point. must be equals to M1 V1 plus M2 V2, that two fragments. Okay, so 12 times 86 must be equals to M1, which is 9, times V1. We already found out that it's minus 86. Okay, that's why it's here. Then plus M2, which is 3, times V2. Okay, this is velocity of 2. And then from here, right, we will be able to find what's the velocity of fragment 2. Okay, so we make use of momentum to find out the velocity of fragment 2. Okay. So after we find out the velocity of fragment 2, we can find out what's the change in energy already. They are moving, right? They have kinetic energy. At that point, you compare after the explosion versus just before the explosion, the energy that they have. So energy released in explosion must be equals to final energy, or rather final state energy, minus initial state. So the final state, we have the first two terms. So this is the final. And this term here, right, is initial. Okay. So we take final minus initial. You see this half mv square, and then this half mv square of the fragment 2, fragment 1, fragment 2. After explosion, that's why we have these both fragments, right? And then they are traveling away at some velocities. So there will be a value for this. And initially is before explosion. It's a 12 kg mass, and then it's traveling at some initial. Okay, so the whole thing will have some half mv square, which is the kinetic energy. If you take the final minus the initial, right, the difference in energy will be the energy released in the explosion. Okay? Then you realize, oh, you put in the values. Delta E, which is the energy released, right, is 5.33 times 10 to the power of 5 joules. Okay, so this back part here is conservation of energy. Initial confirm you have less energy. Final, you have more energy. The difference, right, must come from the energy released from the to give the system so much mechanical energy. Okay, any questions? If not, then we continue. I think this is the last example. The boy on boat and a turtle. A 40 kg boy stands at one end of a 70 kg boat that is 4 meters in length. The boat is initially 3 meters from the pier. The child notices a turtle on a rock near the far end of the boat and proceeds to walk to the end to catch the turtle. Neglecting friction, where is the boy relative to the pier when he reaches the far end of the boat? Will he catch the turtle? Assume he can reach out 1 meter from the end of the boat. So this scenario is depicted here. 3 meter from the end, the boat is 4 meter, and he is starting from one end of the boat, assuming he's at one end. So you can imagine this boy, because there is no friction, no resistance, no nothing, right? When this boy moves to the right, what will happen? The boat will move to the left, correct? When you move to the right, boat will move to the left. Okay. If you have a canoe before overseas, that means on a rather light and small boat. If you get onto the boat already and you try to walk, you'll realize the boat is also moving, right? Of course, it doesn't move as much because got water resistance. But it's because the boat is also moving, which a lot of people never account for, right? That's why when they walk on the boat, they'll fall down. Okay, because they never expect the boat. But the boat will move. If you know that the boat will move, right, you think about that. I don't think you'll fall down because you already account for that in your head. Okay. So what happens? The boy move right, the boat move left, such that the CM of the system of made out of the boy and the boat, it will remain at the same place. All right. So that's sort of like the criteria. So this is initial state, initial state. The bottom of the picture is the final state. So the boy already walked to the end of the boat. Then the boat moves some distance to the left. But the combined CM, right, must be at the same location. Okay, must be at the same location. So we make use of this fact to solve this problem. Taking the pier as origin, x cm must be 40 times 3. This is the mass of the boy times distance from the pier, plus the mass of the boat, which is 70, times distance from the pier. This is 4 meter, right? So distance from the pier will be 3 plus 2. Okay? Then divide by the total mass. It's 40 plus. We already know the XCM already, right? So now we make use of this value to find out where the boy will be. So in this new scenario, right, let's assume the distance from the pier to the boy will be x. Okay. And then the distance from the boat cm to the pier will be x minus 2. Because we know from him to the cm of the boat it will be 2 meters, right? Confirm is 2 meters. So this one is confirm x minus 2. So with this x, right, we use this x, we can write out another expression for xcm. So xcm in this case must be 40, which is the mass of the boy, times x, plus 70, which is the mass of the boat, times x minus 2. Okay, and divide by the mass. If you equate this to this, right, that means this xcm, if you go and plot together, go and substitute and equate them together, you will only need to solve for one thing, which is the x. Okay, then you will find that, oh, x equals to 5.5. So he is now at 5.5 meters from the pier. Okay, actually, this is the main thing to calculate. The new center of mass, the center of mass of the boy, which is where he is. Okay, but of course, to answer this question, they tell you the boy can reach out the hand 1 meter, right? So 5.5 plus 1, he will be 6.5 meter from the pier. Can he reach the turtle? And not, because the turtle is 7 meter away. Okay. Any questions? So after this is supplementary questions. Also, yeah, go and have a look. Go and have a look. And also, you have some tutorial questions lah, which the next lecturer, the flying lecturer, will go through with you all. But of course, and I know not all of you have the time lah, have so much time. So, but at least go and look through all the questions and try to do a bit, okay, before the lecturer goes through with you all. So maybe can try to start looking at them already lah. The concepts that you know, you can start trying. Okay, if you read then you don't know what the question is talking about, chances are that we haven't gone through the topic yet. Okay, any questions for this topic? Motion of a system of particles, center of mass. Okay. Some examples I use, like this boy and the turtle thing. Maybe some of you think, hey, I'm studying engineering dynamics. Why am I looking at a boy and a turtle? Makes no sense. Okay, but actually all these, they are related to engineering dynamics. Okay, so when you deal with engineering stuff, all these will also apply. It's exactly the same concept. You can also think of it as even this whole thing. Right? Let's say you have a boat. You want to design a robot arm on a boat that can move from one end to another end, travel in water on. Maybe can use for disaster, right? Saving people. Autonomous robot on a boat that can move to the front and back. This one will also apply. So as an engineer, all these concepts will make sense. Okay. Now the time is around 9:41. Actually, I plan to stop here. So 11, we'll go through the next lesson. Okay, so now we finally get to stop early. So y'all can go and have a rest. But whoever want to ask me any questions, right, can stay here and ask me. Okay, I'll be here until nobody want to ask me any question. Okay, so any questions? Oh yeah, regarding attendance, let me check. Okay, attendance, I think all of you are here, except for Ravi Kumar. Are you here? Ravi Kumar, because I don't think I see you. But anyway, if you are here and I miss you out, remember to tell me. So I will submit this attendance. Okay, so questions. Curious, will you be going through the assignment with us as a class? Um, I can go through it generally again. Okay, but I won't tell you all too much lah. Basically, it's an assessment. So actually, I plan not to go through with you all. Okay, basically, it's an assessment to test you all. Okay, but assignment one, assignment two, maybe after sometime after the break. Okay, anyway, next week no lesson, right? So sometime after the break, we can look at it again. Okay, but I won't be saying too much lah. I won't be saying too much. Okay, so don't expect me to say too much lah, of course. Yeah, but if you got any concepts that you don't know regarding the notes and the supplementary questions, all this, right? Yeah, I can kind of clarify with me because all these concepts is what you need to use. What you need to use. Okay. Okay, Hewa. Then is 11 the last lecture material? No, 11 is not. I only upload until 11. I'll upload more. It's until 19. Until 19. Okay, so we got 3 more, right? So we will be doing, when we come back, we'll be doing 11, 12, 13, and 14, 15, 16, 17, 18, 19, like this. Okay, we only have 6 sessions, right? We are left with 3. And I would expect the other 3 to end also earlier. So earlier. Only the front 2 where we take longer time, right? Will the exam be covering all 19 chapters? Yes. Will be covering all 19 chapters. Actually, if you go to your Canvas and see, right, you see those tutorial questions, those tutorial questions. That means the ones that the fine lecturer will do with you. Those are sort of quite similar, I would say similar to what the exam will be asking you. Similar style lah. Of course, you're not going to get similar question lah, similar style. So you're going to have a question and then probably an image that looks like that, okay, to ask you something. How many questions? There are 7 questions to be completed within 3.5 hours. So each question on average, you will need to complete within 30 minutes. Yeah, half an hour. Hmm. Okay, and then also yeah, the formula sheet, I have published it already. Okay, I think that's the formula sheet that I didn't create a formula sheet. So the formula sheet should be the one that they use for previous runs. And I think the coordinator for this module, right, which is from RMIT, I think he wants you all to use the same formula sheet. So I have already published that. The last lesson, we will go through the formula sheet. Okay, but by the last lesson, you should know what's everything in the formula sheet already, even if I don't go. Okay, the concepts you should all know already. Maybe the alphabet, sometimes use T means kinetic energy, sometimes use K, but this kind of thing confirm know already. Is the exam an open book exam. No, it's not open book. The formula sheet will be provided, but it's not open book. Okay, you'll be provided with that formula sheet for you all to do. And also for the how the setting of the exam, right? How is it conducted? They haven't confirmed yet, but they will email you lah. So the admin will email you. That one they will liaise directly with you. I will not be invigilating the exam also. So they will be proctoring the exam. Yeah, perhaps it's physical. Maybe they will say something like, oh, it's physical, then bring along this, bring along that, then go to where, that kind of thing. That one is not decided by me. Okay, any more questions? Yeah, if not, then thanks for attending the lecture. Okay, go and have a good rest. Yeah, so see you all next week. Next week no lessons. Okay, next week no lessons. So see you all the following week, which is also online. Which is also online. Okay. Yeah, Gerald, no problem. Yeah, see you. Is there any answer for the tutorial? So, Muhammad Azhar, the tutorial, right, is the there will be solutions lah. So the flying lecturer will go through with you all, and I would think she will release the solution lah, but I have no say because that's her portion. Okay, there would be solutions, but I don't know whether it will be released to you all. So when she goes through with you all can ask her to send you all the solution or something like that. Okay, yeah, thank you, Andrew. Yeah, thank you, Daryl. The assignment one need to use some working model simulation. Okay, this one I in the first lecture I got say, which I will talk about it. Again, I'll remind you all. Basically, right, to simplify things for you all, I say just do the analytical part. So the simulation part, right, I totally remove for you. You all don't need to do the simulation at all. Okay, don't need to do the simulation at all. Just do the analytical part. Simulation means you have to use some software, then key in the values to find out, let the software compute for you. Okay, that is simulation. Analytical means you do working, like what we are doing now, like how we are solving the solutions, examples, all this, right? Using equations after equation. This is analytical, okay? Which is what you need for exam lah. That's why I say just do this, just do analytical part. Okay. So when she flying, she will go through all the tutorial. Yes,